And there are other things to consider. So, for instance, one has to model the noise sources, the kind of production rate of photons, and the detection. So down here the detectors and so on. So with such a kind of a noise transmission line model, a transmission line model which includes noise and so on, one can come up with kind of curves where one, for instance, can read off the ideal or optimal production rate of entangled photons. So this would be the entangled photon source up there. And it turns out for like a typical detector, let's say about 500 dark counts or 500 photon detections or dark photon detections per second, that the entangled photon source would have to produce around 5 million entangled photon pairs per second. So,
if you're creating all these extra photons, let's say someone's just standing next to the receiver and they have like a mini receiver, will that kind of interference be able to be detected?
No, but that's not necessarily detected, but also it doesn't matter. Because photons are indivisible, so you can't split them up. So what happens if the source sends one photon at a time, let's say, so in the ideal case, one photon at a time, then the photon will either make it to Bob, the planned receiver, or to the other one sitting on the side. But it will never turn up as an event in both receivers. And so that would be an event that would be just like a photon which got lost on the way. So that's why these kind of quantum transmissions are inherently secure. Those photons you can't split them up, split off the information and without disturbing them.
But if you have to send 1,000 photons for one to be received, doesn't that imply that you have like I don't know.
So
it
what do you
seems
mean?
Like someone could be scooping them up, receiving the same signal.
Yeah, but after the transmission, Alice and Bob talk about which photons made it through.
Okay.
And so in the end, they only work with those events where the photon really got received at all. And the other 1,000 other photons which were sent by Alice, they get discarded.
Okay.
All the other events, they just don't talk about it anymore. So, of course, there could be attacks where somebody tries to put a beam splitter into the arm and tries to split off photons, so there can be if a source is not perfect, it will create two photons at the same time. And so there are certain thresholds which have to be taken care of. So in the ideal case, there's absolutely no problem. In a practical implementation, one has to worry about that. But it can be, but that's kind of solved. We put it that way. We know well what to look for and what to take care of to make it secure. So for instance, for the ESA system with the entangled photon sources, we have come up with an outline or design of such a quantum payload. The most striking feature are the two telescopes up there. So one considers having an entangled photon source, having two telescopes to send the photons into different directions. Then there are optical arms and on either side for laser beams, which are used in addition, as well as the quantum parts. And one of the main features up here would be an entangled photon source, where one photon goes this way essentially and out through the telescope, the other one here. And the rest is mainly supporting systems like data acquisition or classical, so strong laser beams for communication, also finding and pointing the satellite. So the receiver and the satellite will have to look to each other, and they will use lasers as as a guiding star essentially. Also, there's a fine pointing mechanism there, which is needed for correction, and will have to be, the beams will have to be pointed in the microradians kind of resolution. And one of the main achievements also in the lab done a couple of years ago was to show that it is possible to actually make such an entangled photon source which can reach those requirements of 1 million pairs per second. And all of that on with a small form factor. And so we developed this, or it was actually developed before already, but we improved the source for entangled photons based on a new type of crystal, PPKTP, a very old crystal, which has a very high efficiency. So what happens here is that there's a laser, a 405 nanometer, and the laser beam runs along here, is focused, and essentially comes into this type of nonlinear crystal. And in the nonlinear crystal, one of those blue photons can decay into 2 red photons. And this is a spontaneous decay where those entangled photons are created. So here, this is a particular configuration called a Sagnac, where the same kind of crystal here is pumped from the 2 sides at the same time. And so we get the 2 photons, they will come out here, one on this arm and the other one on that arm. But we don't know where they come from. So if they're created in this side, then one is H and one B, as is from that side. However, if they come from that side, then the H will come out here and the V on this arm. But if they were produced on that side, then this one would be the V and that one would be H. And this leads to, so we get one photon here and there, but we don't know from which direction they were created or through which direction. And that leads to this entanglement. That's essentially kind of the state-of-the-art entangled photon source at the moment. So with such a concept in mind, this is a study together with space industry. This kind of payload design concept was made. This is a payload which could fit onto the International Space Station. And most obvious are the 2 periscopes down there for pointing the 2 beams in essentially 2 pi. And inside it will contain all the required modules like the sources, the quantum source and laser sources and electronics, which are needed for the whole system. And I'd like to point out a scenario: if we make the full-fledged model, it would be around 90 kilos in weight and require 200 watts in power, which is for the space station apparently all feasible and possible. But if one thinks of a separate satellite, that's actually too much. And this is also what is going to be studied here in this Canadian study, to put all of this compressed, compactified onto a microsat, where we're talking maybe in the tens of kilo total and much smaller in size. Kind of slightly disordered. So feasibility of all of this, we talked already about the transmission on those islands. This is again the receiver on Tenerife, this receiving station, a 1 meter telescope which points horizontally across, and down below